All right, in this video, I'm going to talk to you about frame of reference and relative motion. So the frame of reference is simply a way of describing position, velocity, and acceleration from a given location. Now, in this course, we will be using what is referred to as the inertial frame of reference. This is a frame of reference that is not accelerating. In other words, this frame of reference is either stationary or moving at a constant speed. This motion can be described by an observer, but it's relative to their frame of reference. That's what this video is all about. So let's look at our ladybug here at the bottom of your screen. The ladybug is stationary on the ground and observes a bocce ball that comes flying by. Okay, again, the bocce ball comes flying by, and we want to describe this motion relative to the frame of reference of the ladybug. Here's another ball flying by, and it's moving with even a greater speed than the red ball was. So we have a way to calculate relative motion for the velocities of objects relative to the ground, relative to the earth. Like in this case here, our ladybug is stationary on the earth or the ground. And that would be that the velocity of object A relative to object B is equal to the velocity of A minus the velocity of B. And we are talking about vector quantities here, so both magnitude and direction need to be taken into consideration. So let's go ahead and do a calculation given that we know the speed of the red bocce ball to be 8 centimeters per second, and that's in the positive direction as it flew from left to right across your screen. Velocity B will always be that velocity of the frame of reference. In other words, in this case here, our stationary ladybug has a velocity of 0 with respect to the ground or earth. Okay, again, I'm going to box this and make sure you understand when using this equation, you will be assuming that the velocities of these objects are with respect to the ground. That is very important, and I'll expound upon this in a later video. Okay, now let's go ahead and calculate this. We have the velocity of our reference frame, which would be the ladybug that is stationary, and then we have the velocity of the red bocce ball that flew across the screen at 8 centimeters per second. So in this case here, we would get the velocity of the bocce ball with respect to the ladybug would be 8 centimeters per second. And I know you're thinking, wow, why is he making this so complicated? Well, guys, really, I will get into some more complicated problems, but this is all fairly intuitive. So a lot of times you'll see that it makes sense. Now, let's go ahead and consider this ladybug moving to the left, observing a bocce ball moving to the right. Okay, so the frame of reference moving to the left at a constant speed, bocce ball moving to the right. Okay, the frame of reference again is inertial, which means it's either stationary, as was the last example, or it's moving with a constant velocity, as will be the remaining examples. Okay, so let's use this very easy equation and calculate the velocity of the bocce ball from the reference frame of the ladybug that was moving to the left. Remember, vector quantities, please pay attention to signage. The red bocce ball was moving to the right. The ladybug was moving to the left at 4 centimeters per second. So our relative velocity here is 12 centimeters per second. I want you to think for a minute about driving down the road. Okay, you're heading to the north and you pass another vehicle going the same speed and it's heading to the south. Well, if you look over at that instant, the vehicle heading to the south flies by with what appears to be twice your speed. Okay, so think about these examples that we experience in everyday life, and I'm going to refer back to the vehicle example repeatedly here. Okay, now let's look at this. A ladybug moving to the right, a red bocce ball moving to the right. The red bocce ball is moving to the right with a greater speed than the ladybug. However, they are both, in this case, moving to the right. So back to my vehicle example. All right, now I'm heading north, and another vehicle, two lanes heading north, and I look over, and it's also heading to the north, but I'm going a little bit faster than this guy is over here, not by much, a little bit, and it takes me quite a while to actually safely pass that particular vehicle. All right, so think of that example here. Let's go ahead and calculate the velocity of the bocce ball relative to the reference frame of the ladybug, which was moving to the right at a constant speed. Signage matters. They're both moving in the positive direction. This time we get a velocity that is less in magnitude than the previous example. Previously, we got 12 centimeters per second when they were moving in opposite directions. Here we get 4 centimeters per second when they're both moving in the same direction. However, one was moving 4 centimeters faster relative to the frame of reference, i.e. the ladybug. Now, guys, we can also do this with vectors. So some students find this to be the easiest way of them all, and that works. That's wonderful. So I've drawn an arrow to represent the magnitude and direction of the red bocce ball. Now I've drawn an arrow to represent the magnitude and direction of the ladybug. However, recall from unit not, when we subtract two vectors, we're actually adding the negative of that vector. So to do this correctly, I have switched the direction of this second vector for the ladybug. Again, when you're subtracting vectors, you actually add negative vectors. And I've shown that here on the screen. And now I can show my resultant vector to be 4 centimeters per second. And that becomes very evident now by simply using vector addition, vector subtraction in this example. Now, here we have two bocce balls moving to the right, one red, one blue, but on the blue bocce ball, we have a ladybug. Okay, so if we want to calculate the velocity of the red bocce ball from the reference of the ladybug, which is on a moving blue bocce ball, it's pretty obvious, guys. They're both moving with the same speed relative to the ground because the ladybug wasn't moving on the bocce ball. So their speeds, let's say 8 centimeters per second, were identical. And so, by using this method here, we can simply say, oh, okay, both moving to the right, 8 minus 8 is 0. And that should make sense. Go back to my vehicle example. Now I speed up. I'm right beside a vehicle and I let off the gas and I go at a constant speed, the same speed as the other vehicle. And I look over and I wave, hey guys, how you doing? And they don't appear to be moving at all from my frame of reference because we're both going the same speed relative to the earth. All right, guys, so in this video, we started to look at relative motion and frames of reference. In the next video, I'm going to get into some more complex examples of relative motion and frame of reference. I'll see you guys in class.